Okay, now we're going to start talking about polymerized monosaccharides. So we're going to start building up and talking about more complex carbohydrates. So we're going to work on our polysaccharides or glycans. Okay, so this is chapter 7.2 in your textbook. So when you start linking multiple subunits together, so the first thing to note is that you can link the same sugar together over and over again, and you get a homopolysaccharide, or you can link multiple sugars together in whatever order, and you get a heteropolysaccharide. So we describe these polysaccharides, first of all, based on their composition, and mostly what we're going to find these types of polysaccharides in, their use is for fuel storage. So this is how we store our monosaccharides so we can break them down later for fuel. And we're talking primarily in animals. We're talking about glycogen. That's how we store our fuel. And in plants, plants store their fuel as starch. Delicious. Okay, so you also can notice that when you start linking these molecules together, you can get a linear chain or you can get branching. Right? So in branching, you start forming glycosidic bonds, for example, between an anomeric carbon and carbon 6. So a carbon that's hanging off the ring already. That's how you start a branch point. And so the more branching you have, the more monosaccharides you can stick in a concentrated amount of space. And that's going to be important. And that's also going to be how we differentiate between glycogen and starch. So let's talk a little bit specifically about glycogen and starch. So they're similar to one another. They are both polymers of D-glucose. Okay, so they are homopolysaccharides. They are all composed of D-glucose. But they do differ in their degree of branching. Okay, so it turns out that glycogen in animals is way more branched. So you have lots of glycosidic bond linkages that become branch point. And that's going to be important. Again, if that bear is chasing you down, having all of those branch points allows you to work on breaking down that glycogen really, really quickly so you can release your glucose to fuel your little legs to run away from that bear. Okay, so let's look at the structure a little bit. And we're going to focus in on starch, since again the only difference is the degree of branching. So let's take a look. So starch is composed of two parts. Amylose is one part. That's the linear chain that's within it. And then there is amylopectin. So amylopectin is the branched part. So where you start getting branching of the sugar chains. So if you look here in part A is amylose. So we can look at these bonds between the D-glucose molecules. So we see we have a bond at carbon 1, which is the alpha carbon. So that's alpha 1. And it goes through the hydroxyl group of carbon number 4. So the glycosidic bonds in amylose and in amylopectin are going to be alpha 1, 4 glycosidic bonds. Then if you look at the branch points, those instead, they're still going to this anomeric carbon here, carbon number 1, but they're forming a glycosidic bond to the hydroxyl group on carbon number 6. So those branch points then are alpha 1, because we have to say the stereochemistry at the anomeric carbon. These are alpha 1, 6 glycosidic bonds. And this is going to be important for the three-dimensional structure and for the general properties of these molecules. So in terms of three-dimensional structure, these glycosidic bonds yield, wait for it, none other than a helical three-dimensional structure. So the alpha 1,4 linkages, just based on how they go and the overall structure of these rings, you end up with a three-dimensional structure that is helical to an extent. So let's talk a little bit about why amylopectin then is going to be good for fuel storage and glycogen as well. So first of all, it's going to enhance glucose uptake. right? So we're going to be able to get more glucose uptake into cells. So glucose in the blood is about 5 millimolar. And when we talk about transport later on, you certainly can't, it gets really difficult to bring in more glucose past that 5 millimolar point because you equalize the concentration of glucose outside and inside the cell. But it turns out that as you instead take those glucose molecules inside the cell and you polymerize them, you're essentially removing glucose. And so that allows your cells to bring more glucose in. That's Le Chatelier's principle. So we are enhancing glucose by removing it to form glycogen. The next thing that matters is glycogen is essentially not as soluble as glucose. So then it doesn't contribute to the cell osmolarity. So the osmolarity is the concentration of all the particles that are dissolved, and it affects the direction of water flow. So the greater the osmolarity, the more water would flow towards those particles. So you can imagine if you had a really high osmolarity in your cell, water would flow in and it would pop. Okay. The next pro for storing our glucose as glycogen, or amylopectin if you're a plant, is that it takes up less space because it's not as solvated. So if you take a glucose molecule, it's got all those hydroxyl groups, they're all going to interact with water molecules. But as you start breaking or start blocking some of those hydroxyl groups by putting them into glycosidic bonds and forming this three-dimensional structure, you just don't get as much solvation. Less solvation means less space. And again, finally, when we talk about our bare chasiness, we end up with multiple non-reducing ends. Okay? And so the more non-reducing ends we have, the faster we can break down because the enzymes that are breaking down glycogen recognize these non-reducing ends. So every time you have a non-reducing end, the enzymes can come in and release that glucose molecule so that it can be converted to fuel. So these are some reasons why, physiologically speaking, it's good to store our glucose molecules in the form of glycogen. So let's take a look now at another similar molecule to amylose, and that is going to be cellulose. Let's take a look. So this is the structure of cellulose. And if you look at this, you should come up that it has a very similar glycosidic bond. It's still between carbons 1 and carbon 4. But unless you're a termite, you cannot break this down. So humans cannot digest cellulose. So I'll give you a minute, pause the thing, and see if you can really look at this structure and figure out how cellulose is different than the polymerized glucose units in amylose, which we can break down. So it's still 1,4 bonds, it's still D-glucose that's polymerized. What's different about it that makes it that we can't digest it? So hopefully what you came up with is that cellulose, the glycosidic bond at carbon number 1, is a beta anomer as opposed to an alpha anomer. So it's that stereochemistry around that anomeric carbon that prohibits our enzymes from recognizing. And we saw that with our nut and bolt activity for enzyme activity. Enzymes are very stereospecific in terms of the chemical reactions that they can catalyze. And in terms of three-dimensional structure, you also get a much more sheet-like structure with cellulose because you have that beta stereochemistry. It's the alpha stereochemistry that gives you a more helical three-dimensional shape. Okay, so you can read in your textbook, I would say, just the rest of this section, 7.2, maybe from page 259 to 263, if you're interested in learning about some more of the common polysaccharides, for example, peptidoglycan or heparin or polysaccharides like that. I'm not going to spend any more time going over their specifics, but you now know the general characteristics of polysaccharides.